Hey everyone, I'm Seshendranath Balla Venkata. I'm a senior manager and I build data products and that takes care of data engineering with Comcast. So today's talk is about cloud computing costs, how we will save millions of dollars optimizing AWS EMR and Databricks workloads. So let's dive into the talk. The agenda for today's talk is we'll deep dive into what is Databricks and what are the Databricks cost optimization. Then what is AWS EMR? What are different types of AWS EMR features is available and offerings are in market. And we'll look at what are the AWS EMR cost optimization. So what is Databricks? So Databricks is a cloud-based unified analytical platform which is built on top of Apache Spark. So Databricks bring ease of use on top of Apache Spark, where it has like a lot of UI capabilities on top of it, and it can leverage for data engineering and machine learning and huge big data processing. And the key features of the Databricks are Apache Spark optimizing. So if you see like open source Apache Spark versus Databricks version of Apache Spark, it's more optimized and you will see lesser errors running huge workloads. You'll not see the workers dying in middle when you're running on Databricks. And it offers one feature called the Delta Link, where it provides asset compliant on your data set. Like it's more of LTP offering from Databricks. So Delta is more of like whenever there is a change happens on your system, it will capture that and it will maintain the metadata for it. And you can pull the transactional information and it supports the asset. And it supports serverless compute as well. This is a new feature which they launched. And as I said, Databricks can be offered on any cloud provider like AWS or Google Cloud or Azure. So right now these three offerings are there. And this Databricks will provision on top of it and you will process the data for your compute and analytical combinations. And it offers collaborative notebooks where you can go and write your notebooks and you can deploy that, whether it's for data engineering or for data science or ML workflows. As I said, it's a multi-cloud support, like where you can have AWS, Azure, or Google Cloud. That's the key features. If you look at the bottom, there is a picture for where it has bricks and it will do the governance with all these cloud providers, and it provides a business intelligence, data warehousing solutions, AI, ML, data science solutions, ETL, and real-time data processing, and within their tool. Why we will use Databricks, right? So that's a good point. One of the biggest advantage with Databricks is like cost optimization, where you can run your workloads using Databricks and you don't have to worry about provisioning these clusters, where to get these resources and all of that. You simply focus on your business use case and Databricks will take care of orchestration and provisioning of these resources. It's a high performance. So one of the things is, like as I said, it's a optimized version of Spark, and it has their engine called Photon engine, where it runs SQL and Spark updates for particular use cases. Not all use cases are supported with Photon, but that's really extensively performance compared to general Spark, and it's written in C++. So it optimizes the memory really good. Then it's a collaboration friendly where you write your notebooks and you can share across engineers, and it can in real time you can do real time development and seamless integrations with all these cloud providers. So that's on a high level like what Databricks is offering right now. Then we look at Databricks optimization into like multiple layers. It's not like one simple point where we can optimize. There are multiple ways we have to do it. So the first one is like we need to review EBS usage. So what is EBS, right? So whenever you launch your node or cluster, the data when it processed, right, whenever it goes out of the memory, it starts writing to the disk. So most of the nodes comes with the internal disk itself. If it is not there, it will use the AWS EBS storage. So most of the time it's a default storage available on the nodes. So if you look at disk storage is used for shuffling, as I said, and checking your instance type, allocate disk is very important. So when you use i3-4x large workers has 3.6 TB of local storage. So we don't have to use EBS volumes if you are using inodes, but still people go and provision EBS volumes where you're paying additional cost to it. So EBS cost per job is like storage cost plus IO cost and snapshot cost and data transfer cost. So like everything comes into EBS. So it might look very small initially, but when you're learning huge amount of jobs and we are paying in millions, this one contributes a huge. And when you can tweak this one, you can save up to 50 to 80% of your savings. Understanding auto scaling pitfalls, right? So saving up to 25% is possible. So basically, like whenever we have fluctuation in data and it's seasonal, right? We don't like how much data we'll get in. So normally what we do is like we'll go and enable auto scaling. But whenever job goes on auto scale, whether it's a upscale or downscale, it keep on calling the config where the calling for config is a cost related thing, right? So don't use this auto scaling unless it is really required. If you know the history of the job, keep it simple, keep the not dynamic and static resources. That way you can save on the auto scaling. Reduce AWS config cost. This is like subsection of auto scaling, as I said like previously, where whenever you keep on calling this AWS config from Databricks, it creates a lot of cost recurrently for upscale or downscale of your resources, whether it's the EBS volumes or increasing adding the nodes or reading the nodes, anything, right? It's always uses the cost and it's a bombard to the job. So it's always recommended to use right appropriate instance. That's the next point. So move appropriate workloads from M node to I nodes if it is like where you can get like internal volume where it will help with the EBS volume. On top of it, you can know what's the cost savings or cost breakdown for M node versus I node, right? So choosing the right instance is the key here. We miss a lot of savings by choosing the wrong instance. For example, M5 4x versus i3 4x large. Both has its own. You need to understand like why we are choosing that instance rather than simply blinding and going with the recommendation. So we need to have like really good understanding of choosing instance. The last one is spot versus on demand. Most of the workflows, it depends upon if you are running a higher SLA job, then you can run on demand. If you are having a lower SLA job, bank on cheaper spot instance where you'll go and bid for the instance and you get it, but the chances AWS can terminate if they get a bigger bid is high, but still you have a lower SLA job which can be resilient if you restart, and if you run one more time, still you will save money. So this happens very rarely in AWS instance where someone comes and grab your resource, but still you can save a lot of money on that. So there are a few other optimization challenge things which we can do, right? So using the right number of shuffle partition. So the key with any of your workloads, particularly the data workloads, is like we should not have the shuffle and the amount of data written to the disk and the amount of data shuffle over the IO should be very minimal. So we need to look at like when you're doing huge amount of aggregations like group by joins or reduced by key, the key should be distributed across all the nodes. That way the power of distributed computing can be utilized to the fullest. So the partitions is very important. How many shuffle we can do is very important. Most of the engineers know about this one, but most of the time they overlook this one. And we need to look at the UI and see like how much data is being spilled, how much data is being shuffled over the network and all of that. Spark has like really good UI to showcase all of that. So it's always recommended to have 2 times of number of cores that keep that as your shuffle partition. That way it's like evenly distributed across all the nodes. And caching, right? Like people overly use caching even though it's not required. So Spark is a DAG where it recalculates everything. So if you wanna cache it in the middle so that it will not recalculate the entire DAG. Look at the UI to understand like how much activity is happening with the garbage collector, how much cache is required and all of that, and use cache properly. And duplicates is one of the biggest problem where you may see all the data going into one node or maybe the key is not unique. So there are multiple ways you can reduce the duplicates before you process it. Get all the duplicates into one data frame, process on remaining everything and just union it. There are like multiple ways you can do it. One of the technique is called salting, where you will take the key, add a unique value to it. That way you can make sure that the key is distributed across all the nodes and it can process it. So this kind of, there are a lot of ways you can eliminate the duplicates and reduce the cost in running these jobs for a longer time. And the last one is establish a robust data lifecycle and cost system. So defining the life cycle policies on these data sets and how much these jobs need to run and all of that. That's very important. And you need to keep monitoring these jobs. So sometimes like we might think, okay, this might be using this much. If it is having enable with auto scaling, all of that, we don't only call this small nitty-gritties of what's happening with the job breakdown. So we need to look at all of that and keep a key on that and keep an alert on it. If it crosses that threshold, get an alert and start looking at like why the job is performing like that. So let's now dive into what is AWS EMR. So AWS EMR is a cloud-based Databricks processing offering from AWS, where you can run Spark-based or Hive-based jobs on EMR, right? It's equivalent to like when Hadoop started, they released this EMR, Elastic MapReduce, where you can launch your MapReduce jobs or Hive jobs on it, and it'll run on EC2 instance. And it evolved over the time. And a lot of companies and a lot of teams use this one for different purposes. So there are three flavors to AWS EMR. I'll talk about the difference in a minute, but I just want to explain like what are the three flavors we have or three offerings we have on AWS EMR. One is like the legacy EMR on EC2. That's when you have large scale workloads and you need to process all of that, you'll use EC2s. But like the cluster management is like very tedious. Provisioning, scaling, and monitoring is like very hard if you're doing with EMR on EC2. Then the second offering is EMR on EKS, where you will launch your EMR on EKS, like Elastic Kubernetes services, where you will run all these jobs over there. The problem with this one is like it's more complex to set up the entire infrastructure. So that is a problem, but like the scaling up and managing the workflows and running the workflows is like you can do it at a scale. The third one is EMR serverless. This is a new offering which started hitting the market from last couple of years, where you can do on-demand, pay for the usage processing. The only problem with serverless EMR is you will not have much control. If you want to tweak something or if you want to change some configuration, it's a little tedious, it's a little complex. So apart from that, the EMR is a game changer as of now. As I said, if you look at the differences, right, the cluster control on EMR and EC2 is little high, then EKS is medium, then serverless is like pretty much low, but we don't have much control on that. Scaling wise, manual, you can automate on EMR, EKS you can automate, and serverless EMR is like completely fully automate. The bit for large scale UTL, for EMR workloads, AML container kind of jobs, ad hoc or busty jobs where you will use EMR. Cost efficiency, if you're going for, this is where the key cost savings you can see. Most of the workflows which we have migrated from serverless EMR to EMR on EC2 to serverless EMR, because that's where we have seen a lot of cost savings, and you'll pay for what you use, right? That's the same case for other two as well, but like in serverless, you don't have to worry about it. It's pretty much following the model of Databricks, where you don't have to worry about like the provisioning and all of that. You just say what you want and focus on your business use case, and AWS will take care of it. As I said, ease of use, obviously, serverless EMR wins the game, but EKS is more complex, but it has, if you really provision, it's to wonder. And EMR on EC2 is like a traditional thing where it's like more versus hard ease of use. We look at how we can save on AWS EMR cost optimization. So the right size cluster based upon the workflow patterns, right? So that's the same kind of thing what we were talked previously with Databricks as well. Like you need to choose the right worker type and right node to provision your jobs. And one of the biggest thing is like the Graviton based instance reduced by 20%. That's a game changer as well, because this Graviton based is a kind of chip which is built by Amazon, and they don't have to proprietary pay anything on Intel based chips. That's a game changer for AWS, where the Graviton runs much faster and they don't have to pay anything on top of that, and they give the savings to the customers. Dynamic auto scaling for efficient resource allocation. As I said, the similar kind of things what we have seen with Databricks. Like we should be very careful with auto scaling, where your jobs are being processed. So we should optimally use the auto scaling. If you don't have to do it, keep it normal, keep it static, and don't have to enable auto scaling. The third one is optimizing Spark performance. As I said previously, Shuffle is very important, where he will not do a lot of IO over the network, or will not write any data to the disk, and where you don't have to read anything. That kills the importance of Apache Spark. So look at that one. Dynamic allocation of Spark executor, ensuring optimal resource usage per job, need to be implemented, and parallelism settings need to be optimized so that you're then, as I said, serverless EMR versus EKS compute. So what we have seen is, like, if you have a, based upon the job type, if you have a job type which is like lower in SLA and don't need, it's fine if it fails and restarts. And based upon that kind of thing, you can select what kind of EMR you can choose. But like we have seen, serverless EMR saves a lot when you're tweaking and running on it with Graviton chips. So we recommend trying serverless EMR in that instance. And data storage and access optimization, like S3, when you read and write from S3, there is a cost to it. And the asset, like how Delta is offered, AWS Hoodie or Iceberg for asset compliant data sets, optimize that to the fullest. Because like whenever you have the asset file system, like the files keep on growing whenever there is a transaction happen on it. So we need to vacuum it, we need to clean it, and we need to keep it like certain versions so that it will not create huge amount of data. So that's again a game changer there. Adjusting the retentions on this S3 objects, not just leaving it alone, will do a huge cost savings. Then automating cluster shutdowns and scheduling. We have seen this huge issue with AWS EMR particularly, where the cluster will be up and it will never be shut down, or it will be keep on running even though there is no workload running. So we should keep on, as I said, like keep alerts on all these workloads. If it's crossing certain threshold, it should be alerted, and we should be debugged and see what's really going on with the SLA and what is going on with the TCO reports. So we need to look at that to identify like what's going on there. So that being said, hope the talk is giving some information of like how you can optimize your cloud workloads. And if you have any questions, shoot me. And